All right, we're right at the start time, 2 p.m. Eastern Daylight, so let's begin. Good afternoon, my name is Ed Nemeth. I'm a Senior Project Engineer at America Makes and your host for today's America Makes TRX webinar series. Before we begin, a little background on the TRX webinar series. As America Makes continues its mission to expand the footprint of additive manufacturing and 3D printing, this platform called the America Makes Technical Review and Exchange webinar series was created. This series allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during the TRX webinar series, please feel free to contact me directly. A few important notes before we kick off the webinar. At the end of the presentation, there will be an opportunity for a live Q&A session. During the presentation, you have a question, please submit it to the Q&A space on your WebEx screen, and we will ask it during that time. We will do our best to get all the questions answered. So let's get started. The title of today's webinar is Additive Manufacturing of Cellular Materials, an Overview of Considerations, brought to us by Arizona State University. Without further ado, it's my pleasure to introduce Dhruv Bhatte. Dhruv is an associate professor at the Arizona State University, where he conducts research in the design and mechanics of additive manufacturing, structures, and materials. Prior to joining ASU, Dhruv spent 2 years at Phoenix Analysis and Design Technologies, a small business in Tempe, where he led the company's R&D efforts in additive manufacturing. Prior to joining PADT, Dhruv spent 7 years at Intel Corporation developing several laser-based manufacturing processes, taking them from early-stage research to high-volume manufacturing. He also spent a year in the automotive industry working for India's largest car manufacturer, Tata Motors. Dhruv has a PhD in mechanical engineering from Purdue, where he developed constitutive and failure models for the prediction of fatigue, fracture, and ductile metal alloys. Prior to this, Dhruv obtained his MS from the University of Colorado at Boulder, where he studied the phenomenon of adhesion in micro-electromechanical systems structures. Dhruv's passion lies in combining theory, experimental methods, and simulation to answering challenging research questions in new and effective ways, seeking inspiration from multiple disciplines. He has over 18 peer-reviewed publications, 2 patents filed, and 1 edited volume to his name. And with that, I'd like to turn it over to Dhruv.
Thank you, Ed, and thank you everyone for taking the time to be here. I hope you can hear me clearly. If not, just drop a note in the chat. Thanks for that introduction, and I'm going to get started because I have a lot of ground to cover. I do want to spend one quick slide on just giving you all a quick introduction to what we do and what I'm doing at ASU. We are the Ira A. Fulton Schools of Engineering. We're now one of the largest, if not the largest, engineering school in the country with over 21,000 students across 25 undergraduate and 39 graduate programs. I work in what we call the Polytechnic School, which is one of 6 engineering schools. We are in Mesa, Arizona. ASU has a few campuses in different parts of Arizona. And within the Polytechnic School, we've made additive manufacturing a real focus with about $2 million in R&D facilities and equipment, including 3D printers. And then we have also been developing, along with other faculty at ASU, I've been developing 4 AM-specific courses around processes, design, materials, and micro-nano AM. So that's really what we do as a school, and my group, which we call 3DX Research, which is really because we think about combining space and composition. So 3D is the space and X is the composition in interesting ways. The 4 themes which you're going to see all of today really is additive manufacturing, cellular materials, material modeling, and biomimetic design. And all of this really comes together really well for cellular materials. So that's a quick background an introduction to us. So today's outline, I want to be frank at the start and say that this is going to be a rushed discussion. I'm going to throw lots of information out there because it started off as a 4-hour workshop that I am still going to do in MMX, and I'll give some details about that at the end. What you're going to see today is a distilled down selection of about 50 slides where I'm going to try and cover the entire topic. But to do this justice, each of these is at least an hour's worth of discussion, if not more. So today I'm going to do introduction. I'm going to talk about specifically about the applications a little bit, and then focus on taxonomy or trying to develop a taxonomy. But then the meat of the talk today is really design, manufacturing, characterization, modeling. So I'll spend about 8 to 10 minutes on each of these 4 topics. And leave about 5 minutes for resources, and hopefully I give you all 10 minutes or so for Q&A. So let's get started. Introduction. I love to introduce this topic, as do many others who teach it or write about it, by deferring to nature, where these ideas first came about, where we see cellular structures represented so well. But I want to draw attention to 2 things that I think are important to this overall discussion around cellular materials. One is the picture on the left-hand side, where you can see how social insects, wasps and hornets and bees, use a range of materials to essentially serve more or less the same function, which is creating storage space for brood, or in the case of the honeybee, for honey and pollen as well. But the point I want to make is that they use different compositions. So we have wax, paper, mud being used in what is essentially a hexagonal structure to create this space. So this use of whatever material you have available but employing structure is one of the key points that I wanted to highlight. And then the second one down here is a sea sponge that's called the Euplectella, or the Venus flower basket. And why it is so amazing is it employs hierarchy at different scales. I'm just showing you the largest scale, but it's a composition of lattice struts, and each of these lattice struts has lots of detail in it. Well, why should this matter? Why am I bringing this point up? I'm bringing this point up because there's something unique about additive that can exploit this for the first time in ways that maybe we couldn't before. If we look at nature, and this is a paper by a professor by the name Julian Vincent, who's one of the pioneers of biomimetic thinking, especially in terms of comparing it to engineering applications. He discussed how nature, when nature tries to solve problems, generally resorts to information, genetic information, but even structure, and how the 2 feed off of each other. When we tend to look at how can we solve a specific problem, energy and material are what we historically think of. And the point Vincent makes is that we should concentrate on those materials with the least energy requirement and the greatest initial variability, and then generate the required functionality by closer control of the information content. So that is why I think, if you sort of take and I won't do this for many slides, but just at the beginning, if we take a very high view, I think the real power in cellular materials is that we can manipulate structure at a very local level and play with properties and have material composition as just one of the variables to generate the functionality that we desire. On a more practical level, we can think of cellular materials as being another step in the evolution of lightweighting. Our first, when we think about how can I lightweight a structure, we tend to look at an Ashby chart or a property chart that looks like this, where we see, the very stiff materials, high Young's modulus materials that also have a very high density. Maybe the metals are up here, and then they come down, and we're trying to get into these low density areas with high moduli, for example. That could be one objective. But we tend to think of it as a material selection problem. The next evolution is to say, okay, I'm going to take that material that I've selected and play with the topology of that. So this is where we think of topology optimization. I'm just calling it more generally bulk optimization. So you're thinking about optimizing the entire structure by making decisions on retaining material or removing it. The third one, and really the focus of today, is cellular materials. And so in the context of lightweighting, it represents the ability to tune material locally and remove essentially what you're doing at the bulk level, in a sense, is what you're doing at a local level. And if you repeat that over the entire structure, you can get some benefit. But why would we want to do that? Because ultimately, I think where we are going with additive, and especially with cellular materials, is in the achievement of multifunctionality. At the level of a structure, this is taken from a review paper in 2016, and I've sort of modified it a little. But if you think of an aircraft wing, we may want some global behaviors, like, the wing should have a max displacement at the tip and so on. It should withstand a bunch of loads, and the center of gravity must be at a specific point, but we also want to have it, enable it, design it in such a way that we can allow for cooling and heating and temperature management. So that kind of system level multifunctionality requires some level of local tuning, and that's where cellular materials have so much potential. So those are my two motivation slides. If we look at coming down the practicality ladder, this is from a 2010 book called Metal Forms, a design guide. Again, I've modified it a little bit. But the point is that cellular materials are already being used. We've seen this. I'm sure all of you all are familiar with this. But this is just a way to think of them as having engineering applications either in the structural domain. I specifically talked about weight reduction, but there could be other benefits that you get in addition, or maybe you don't care about weight so much. Things like strain isolation, vibration control, sandwich cores. On the thermal side, heat exchangers, heat shields. NASA just launched one of their solar probes with a big cellular material heat shield made of carbon. So my point with this, and even in the fluid and the biomedical domain, is that cellular materials are already in use. So the real question becomes, what opportunities does additive enable? And before we talk about some of the design discussions, I want to sort of go a step deeper into the cellular material discussion itself and talk about what are they from a design standpoint, or from thinking about whether something is a cellular material or not. This is one of the attempts I've made to try and come up with a taxonomy that is borrowed from several different people's work. So it's not mine, but I've just put it together in a way that I think helps me think about this. We can, broadly speaking, think about cellular materials as being prismatic. So they're two-dimensional, like a honeycomb, and then, of course, you extrude them in the third dimension. Or we can think of them in terms of being volumetric or three-dimensional structures. If you look at the prismatic structures, they can be either periodic, and periodic structures themselves can be further divided into all these different types. Again, in the interest of time, I'm just going to leave some information there, and I won't be able to go into every single detail. But these are some examples of periodic structures that are not stochastic, where we have a statistical distribution across the structure. So there's a regular shape that is repeating itself, and then you can change that. So there are mathematical descriptions that govern these forms or describe the different kinds of periodic structures you can generate. For three-dimensional structures, we can take a slightly different approach. We can think of them in terms of how would you actually construct it. And this is something that I'm borrowing from a software called Entopology. This is sort of the thinking that the software guides you along the path of. So I borrowed that thinking, and it really comes down to three questions. How do you want to divide space? That's what we call tessellation. Once you've divided this space, how do you want to connect the points in this space, the vertices? What are the elements you're going to use to connect these vertices? And finally, what do you get as a result of that? So broadly speaking, I call them tessellation, elements, and connectivity. For tessellation, these are some examples of the different ways you can take a three-dimensional space and divide it. There are lots of books on this subject of packing and close packing that you can find, especially from mathematicians. That's quite interesting. But for now, I just want to point that out, that that's the first step of thinking. And again, you can, just like the way we talked about two dimensions, we talked about it being periodic or stochastic, you can apply that same logic here. And if it's periodic, are you going to have just one repeating a shape like a regular octahedron, or are you going to have multiple shapes like we see in this picture down here, where there's an octahedron and a tetrahedron? So it becomes a binary system because there are two polyhedra that you are assembling together. And of course, you can have stochastic tessellation as well. The second one is, now that you've created this tessellated space, how do you go about connecting the vertices in them? And that itself is a two-part decision. Do you want to use beams or do you want to use surfaces? And you know, you could do both as well, but keeping it simple, if we went with a beam, you have the question of, well, how is that beam designed? And Topology is one software that gives you options with regard to that cross-section. Do you want it to be circular, square, or have a teardrop shape, which may have some benefits in support and creating self-supporting lattices, for example. You could also think about surfaces, which are essentially planes that you would combine. You may have heard of a family of surface-based cellular materials called gyroids or triply periodic minimal surfaces. They exploit that basic idea. When you think about the volumetric structures, what I'm saying is the first step is you think of tessellation. The second step is you think about what is your connecting entity. And in the third step, you actually make decisions on how to form these connections. So if you take a beam-based structure, for example, you can connect vertices and design your structure like this. Both of these were tessellated in the cubic using a cube to tessellate and divide partition space. But now you can see how there are 4 different ways you can take these beam elements and connect them. And in theory, there are infinite number of ways. And same thing on the surface side. You can develop these equations that determine how they can fill up that space. So I'm going to shift gears into the design aspects, but I just wanted to open it up, you know, and present the opportunity space here for cellular materials. And this is maybe why it's so exciting to a lot of us, is because there's so much you can do with it. And I hope this taxonomy helps one think about it. What does the taxonomy also allow you to do? It may help you develop a nomenclature scheme. So, you know, there's some things that are very popular in the literature: hexagonal honeycombs, octet trusses, Schoen, gyroids. And, you know, one should arguably retain those names. But for everything else, you know, it helps to think of, I like to think of it with this sort of a table. Again, it follows Topology's method and thinking, and that is dimensionality, tessellation, elements, and connectivity, the 4 key things that I just described. And then you can come up with a nomenclature. I was recently pointed to a paper by a gentleman by the name of Frank Zock, and his colleagues have written this paper here, and it's much more rigorous. So it employs crystallographic-like ideas to develop similar schemes for truss structures. So that was a lot of discussion on taxonomy, nomenclature. You may say, why am I spending so much time on this? And I think it's important that we have a taxonomy because ultimately we can relate it to applications. So on this slide and on the next slide, what I've tried to do is take a first pass at listing the different applications that we could have with cellular materials. And then talk about, well, what does that application really need from a cellular material? If it's a lightweight structure, it probably needs high specific stiffness. So you want to achieve high stiffness as a function of mass. And same thing with high specific strength. And what in the literature has been shown or suggested to get us there? Well, it's the octet truss and it's the cubic octet foam. Now, my goal, and you can see some empty spaces out there, is because I have not found a perfect example for everyone. But the goal is to try and use this taxonomy, use this nomenclature to try and make a table of this format where a designer can say, I'm interested in an energy absorption geometry, what should I go with? And this table would tell them. So there are at least 12 in this table, and you know, I've cited the living textbook on additive manufacturing, which I will get to at the end as to how you can access it. So the point is that as I get more information, I will be loading it in there. But this is what we have as of now. So that was the introduction to the topic, and I've already gone about 5 minutes longer than I hoped. So let me try and recover that. The next aspect is design. I teach a design for additive course at ASU, and when it comes to the cellular materials course, these are the 4 questions I ask the students. And I asked them, and we did a project where they had to try and answer these questions because I don't think the answers to these are very apparent. But these are the 4 questions. So somebody gives you a structure and says, fill it with cellular materials to optimize some benefit. These are the 4 questions you could ask. The first one is, what is the appropriate cell shape? I just showed you a taxonomy where you can pick from an infinite number of cell shapes on the tessellation, the elements that you use, the connectivity that you describe. So that is question number 1. Well, once you have this cell, the question is, how do you distribute it through your structure? It could be an aircraft wing. And do you want to go, periodic from left to right, or do you want it to vary? How best can you optimize these parameters, the thicknesses, the radii? These are local parameters that, in some will affect the global response of the structure. How best can you optimize it? And finally, what is the best way to integrate the cellular materials within the structure? Right? It's one thing to populate a structure with periodic cells, but what is happening at the interface? What is happening at the skin, for example? So these are 4 questions, and I cannot give you the answers because I don't think that we have clean answers. But what I can give you today and will be giving you is some thinking to guide, some ideas to guide your thinking. So when we talk about unit cell selection, this is what we mean, and I'm shamelessly borrowing topology screenshots here, but the idea is that we can populate, a beam, for example, with different cells. So that's fairly straightforward. But then to answer the question as to how can you go about making a decision on what is the best cell shape, I'm going to provide a few different avenues. The first one is to use analytical methods. And I'm just listing them here. The details are in the longer form version of this class, or you can go look them up online or in some of the resources I will provide in the end. The first is called Maxwell's stability criterion. The second is using beam theory. If the cellular material, especially the lattices, is an assemblage of beams, you can invoke beam theory and essentially make predictions on properties. And because you develop an analytical result, you can then say, the hexagon performs better than the square. And now you have intuition into why a certain shape is preferable. The second way, and maybe the most popular way, is to, just test. Come up with 8 different cellular material designs and test them. And I'm showing here, for a hexagonal honeycomb, you get these graphs. You can extract the modulus, and I'll talk about that when we get to the characterization portion. But the main idea is you empirically derive relationships, and then you draw conclusions on which is the one that you should select. And one term you will hear a lot of is a scaling law. You can derive equations that are mathematical fits to experimental data that can guide your selection. A third approach, and one that we like to employ, is to ask nature and take a biomimetic approach and say, what examples do we have in nature that are cellular, A, and then B, are optimized for some function we are interested in? And there are plenty of examples like that. And then once you've identified that geometry, you can abstract the main design principle or the main design idea, bring it into finite elements or 3D printing and validate it. So you're not done when you see something in nature. It's the beginning of the process, but nonetheless, it's a great guiding principle to guide your thinking into looking at specific shapes that you might have otherwise ignored. There are 2 more domains where, there's not necessarily a functional connection, but there are ideas that are buried in mathematics and art that are worthwhile assessing. So when I talk about the empirical work, the initial design that you pick could come from these areas, and then you can study them. So why is a K uniform tessellation a good idea? I don't know, and maybe it isn't, but you could look at that, and then you can do it empirically, either experimentally or in computational simulation, and it might yield insights that you would not have otherwise. So getting cell shape ideas from mathematics and art is another powerful way to go looking at it, even if there's no immediate functional connection. You have to estimate that for yourself. The second question that I brought up is cell size distribution. So you select the cell shape for some reason, and now you want to populate it through your structure. And for a simple beam, the simplest way is to manipulate the relative density. The scaling laws that I described before are often relationships between some metric that you're interested in and the relative density. So this geometry has a very small cell size, so it looks denser. It is denser, and this one has a large cell size, and it is less dense. So, and you can do that based on your scaling laws. You could also go with if you go with a stochastic structure, it becomes a little more challenging to decide how you're going to make these choices on distributing your cell size. But the nice thing is you get much more freedom. When you have a regular structure, it's difficult to make all the regular structures fit in unless they're identical. When you take a stochastic geometry, software allows you to do that fit. So this is what we call a Voronoi tessellation. And it looks like soap bubbles because it's that similar idea of filling up space. Some quick ways you can think about cell size distribution is target a relative density, I mentioned that, or you can do a prescriptive modifier function. Note that I'm not saying that there's a necessary connection to function here. These are just ways you can play with cell size distribution. Some strategies on how you could vary cell sizes can come from nature again. One is gradation. Many biological structures have gradation, and this also goes to our fourth question, which is how do you blend with the outside world? Well, bamboo, for example, will have a gradation with larger cells in the middle, and you gradually reduce that cell size and increase your density, and eventually you merge into the skin. Insect wings also demonstrate venation, so you could distribute these cells along a branching pattern, and we see that in nature. Now, of course, wings have this venation pattern, or these veins have many different functions that you may not be interested in. So that's why you have to deconvolute the functions you're interested in. But the point is you get concepts that you may not have otherwise have thought of. And finally, there are many different ways of distributing cells in that, again, as I mentioned before, may not have immediate functional connotation, but through experimentation and simulation, you can validate them. Three ideas in mathematics, and by no means is this complete, is symmetry, the notion of local symmetry as well as on the structural level, cell similarity or fractal geometries, and nesting. These are all different ways you can think about how you want to distribute your cells. The third one, and one of the key ones, because this is sort of a catch-all for poor design in a sense, I'm making that statement loosely, is can you optimize parameters like thickness? So here I'm showing three different ways you could optimize your parameters. You could specify a uniform thickness and specify 1 millimeter, for example, over here, or you could vary the thickness from one side to another, or you could let your solver, in this case, end topology, is actually thickening certain members locally in response to the local environment, the stresses in that environment. And you could do this first, and then you could come and delete all the beams that you're not interested in, for example, and do a reanalysis. So, one of the things that I've always wondered is of these three questions that I've just so far described, what is the relative importance of them? Is it okay if I pick any shape if in the end I optimize my parameters correctly? And I don't know the answer to that, but I wanted to put that out there, this is a very important step, because now you're getting down to the local behavior, which is what we are really interested in with cellular materials to begin with, is that tuning, or it's one of the most powerful things about it, is that you can tune local behavior. The different ways you can think about these parameters, you can do a first principle study, go back to the analytical equation for a honeycomb with a simpler geometry, for example, and you derive an equation like this, which says that the modulus is some function of thickness of the beam and the length and the material property of that material. So one of the things to think about is that when you reduce the length of your beam, the stiffness increases by the cube. Right, so it's very sensitive to the length of the beam and the thickness of the beam. So this is the kind of insight you can get just purely analytically without running any simulation. And you can also look at the corner radius as we have done, and there's some very interesting things that you see specific stiffness increase with small changes in the corner radius. And finally, you can use software to also drive this optimization for you. But there are first principle studies that you could also do that complement it, is my point. Okay, the last question in the design domain is, how do you integrate this? You have a skin or some external geometry. Typically, we start off with some geometry and then we want to populate it with cellular materials. A lot of us want to get to the point where we are mimicking something like bone, right? Where the global structure, the external structure is optimized topologically, and the internal geometry has cellular materials with varying densities at varying locations. So this is sort of the holy grail, or the, one of the goals that we have, at least from a structural standpoint, right? There are other strategies for thermal and fluid-based strategy, but from a structural lightweighting standpoint, this is one way to think of it. And an example here is to start off with a geometry, perform a topology optimization on it, like I'm showing over here, and then use some cellular software to create your cellular structure in it. So it doesn't answer the question about what to do with the skin, and that's where ideas like gradation come in handy, where you eventually blend into the thickness. So again, I don't have time to go into more options with design, but I just wanted to guide your thinking as to those 4 methods and some possible ways of thinking about answering those 4 questions. I want to quickly wrap up the design section by talking about the software implementation approaches. This is as of last year. They broadly fell into 2 categories. On the left-hand side, you can use, Boolean. You have a function, or you have a lattice geometry. You can repeat it in space and then subtract it from your structure or add it to your structure. So most CAD support this, like SolidWorks, for example. You can also use an infilling strategy where you can take a geometry and populate it with an infill structure. And maybe the most powerful aspect is to use lattice design optimization, where you actually allow your software to evolve in response to loads, and like the parameter optimization that I described. So I've just put some names out there for you all to go look at and investigate. But that's the 3 different ways you can think of it. And really, lattice design optimization, if you're looking at getting into functional parts as opposed to, 3D printing a part where you want to minimize material, you really need to be thinking about lattice design optimization. Okay, so I'm going to switch gears now to the second of the 4 sections, and each of these is a little shorter than design, so I hope to still keep us on time, and it's manufacturing. And, first thing to remember is AM, or additive manufacturing, which I've been calling AM without spelling it out. But AM is not the first, right, for cellular materials. We've had other processes, expansion, corrugation, extrusion, casting, biocarbon templates, where you start off with a natural cellular structure and then deposit a material on it, foaming, vapor deposition. So there are other additive, other non-additive processes for cellular materials. So why additive? And there are some advantages, and I think most of you all that work in additive are familiar with these. But one is, maybe the biggest one that I like to think about is the ability to perform local tuning. And I showed those optimization of parameter examples where you can vary thickness locally. The other one is you can develop complex non-stochastic shapes. So with the foaming process in particular, you get, you don't have as much control, and you end up with a stochastic shape, like a bunch of bubbles trapped in a fluid. With additive, we can introduce complexity with a great deal of prescription. As with all additive processes, we pay a low cost penalty. And there's a lot of potential with additive to achieve multi-material cellular structures. If we think about bone, we think about some of the structural cellular materials, tortoise shells, they are using two materials, and that is a big advantage of using a stiff and a soft cellular material that really gets us at least conceptually has a lot of promise. We've yet to demonstrate it practically, I think. But then, with additive comes considerations, and many of these are not specific to cellular. All of these are not specific to cellular, but some of these become more particular or sensitive when you deal with cellular materials. And these are the ones that I'm highlighting here: dimensional accuracy, feature resolution, defects, cleaning, and inspection. And I've got one slide on each of these, and I'm not going to do it justice at all, but I just want to touch upon each of these 5 points. The first one is feature resolution and structure. And what I'm showing here, and I'm sorry I don't have a scale bar, is at the same scale. If you just take a cellular component and shrink it, so each of these pictures is taken at the same magnification, and we're printing a simple two-dimensional honeycomb, you can see at some point it doesn't look like a honeycomb anymore. So if you're relying on CAD geometry and software to essentially make predictions, or if you're relying on hand calculations to describe behavior, it assumes certain things, like, for example, it may assume that you have sharp corners, that and not that your honeycomb is starting to approach a circle. So, for those of us that try and make predictive models, we stumble with this, because when our analytical solutions or our finite element solutions don't match experiments, one of the reasons is this: the CAD model that we started with is not an accurate representation of the feature and the geometry that we are ending up 3D printing. Another one is the parameter size interaction. So, we all know, and yes, it's a general statement that every additive process is sensitive to process parameters. The question is how much. I don't have any evidence or any data to back this up yet, but if you look at 100 micron, this is a laser powder bed fusion wall, a thin wall that's 100 micron thick, and it only employs laser contours. Right, so we've got this laser pattern that scans and goes exactly once and then twice. So you get 2 scans of the contour. If I make it thicker, I start to introduce a raster. And if you remember back to my equation where the modulus scales by the thickness over the length, it also goes by the mechanical properties. And on a bulk structure where you have a lot of rastering and the contours only apply at the skin, that may not be an issue. When you get down to these finer and finer scales, the relative relationship between rasters and contours, at least for scanning or extrusion-based additive processes, could be relevant. So there is that to think about when you get down to really fine structures. So A is how well are you resolving your geometry, and B is what is the interaction of your process as a function of variation in that geometry. The second point is orientation. This is, again, a honeycomb in metal with laser powder bed fusion, and it's oriented 3 different ways without any support internally because it's so small. And you can see that the surface texture and the surface quality is very significantly different. And in a bulk structure, you may say, yeah, I know that. What's the big deal? But in a cellular structure, this could change your thickness by 10% or 5%, and most of our stiffness properties go by the cube or the square of thickness. So a small change in thickness can have a large change in measured properties, especially since this geometry is repeated 200 times or more, thousands of times throughout your cellular structure. So in addition to that, what I just talked about was geometry, but there's also, you may need support, for example, especially if you have large overhangs. Surface roughness, I'm already showing here, varies. Mechanical properties may be influenced. The way your defects are distributed may be influenced. And finally, feature resolution itself. When we print, when we're looking at the structure in the direction it was printed, we see sharp features. When we look at it printed on its side, the features lose their resolution. The third one is something I've touched upon already, is dimensional accuracy. So I like to show honeycombs because they are the best way to understand this concept in 2D, and then you can extrapolate the concept, if not the mathematics, to 3 dimensions. And in 2D, when we look at a honeycomb, we have these wall thicknesses, and I've shown my equation again where this was supposed to be a 60 thou wall. It on average it was measuring 64 thou. Not a lot, and within, more or less within the spec of the machine, but a big deal when it's about 5 to 10% of your thickness, and your stiffness scales by the cube of the thickness. So suddenly your stiffness is in error by 15, 20%. So that's the point I want to make with dimensional accuracy. A quick talk about defects. I don't think we understand defects in cellular materials very well yet. There's some work going on. We know that they occur. I mean, that's a given. But again, the question is, how significant are they? How sensitive are we to their location, their size? How sensitive are we to internal voids versus surface defects, etc. is still an area that we're exploring, or others are exploring more than me. And so it's a space to watch, but one of the points that I wanted to point out here is that we could have process-induced defects that are going to repeat everywhere, right? So we want to avoid those if we can. So in extrusion, for example, with the FDM process, you may end up getting these voids at every corner. So that is a repetitive void, and maybe through a better process design you can eliminate them. And then there are randomly distributed defects which are harder to detect and can be AM process specific. Again, it's not clear that this is any worse or better than sort of bulk structures, but it's something we need to do more work on. Cleaning. There was a beautiful presentation made at the 2015 RAPID conference, which was unfortunately never published as a paper. But the key gist of that was in the biomedical industry that uses titanium implants, they are very concerned with cleaning. So they've done a lot of work. So if you're interested in this, they would be a good place to go look at. And the main purpose of cleaning is to remove trapped powder, but also unseat partially melted particles that may get removed during use. You don't want a lot of loose powder, falling off your implant. So the 4 common methods that people have studied is just air blasting, ultrasonic cleaning, but also sodium bicarbonate blasting and corundum blasting. And from that conference that I attended, the biomedical industries employ a combination of these techniques. So something to consider. Again, I'm not going to go into much more detail than that, but just wanted to bring that up as one of the considerations in the manufacturing process that is more critical for cellular materials than it is for bulk. The last one is inspection. And, by far what the community seems to have agreed upon is that CT scanning is the way to proceed with this. And this is work that a friend recently befriended Professor Anton Duplessis was nice enough to share with me and allow me to use his images. I highly recommend you go look at this review paper. And it talks about CT in additive in general, but there's a lot of discussion on lattices and cellular materials specifically. And these are some pictures from that paper. The one on the bottom gives you a sense of how you can detect these hotspots of defects with CT scanning now in lattices. And the one on the right gives you an idea of how you can export your CT scan to actually do finite element analysis. So this can help us address some of that discrepancies we may be seeing between our modeling predictions and what we observe experimentally. Moving on to my third bit, and I'm going to speed up here because I'm about 10 minutes behind. I apologize for that, is characterization. And I have a few standards out there. There are not many. There are about 3 in the works that are specific to cellular materials. The one that I would recommend if anybody's looking for a standard today is the ISO 13314. It's the closest standard that at least addresses all the points you need to be thinking about. But keep in mind that folks are working on developing something, and if you're interested in this space, ASTM, I believe, is looking for people to help with these standards. But there are not many, and there are definitely no published ones specific to additive at the moment. So in that context, the three things that I want to talk about today very quickly are specimen design, data interpretation, and strain rate dependence, which I don't think has received a lot of attention, so I want to share that today. The first one is specimen design. This is a well-understood phenomenon that structures that have a few number of cells behave very differently from structures that have a larger number of cells, simply because when you test a structure like this, you're interested in the property of the cellular material, but what you're getting a lot of is what is happening on the edges and the free surface. So you're really getting a property of the structure and not of the cellular material. So you have to have a large enough number of cells to extract a stable value that is representative of the cellular material at a unit cell level, as opposed to this geometry. And typically that's about 10 in all directions. This varies depending on what loading direction you have and what cell topology you're selecting. It's a good idea to use simulation and validate that you've reached a stable point. It's almost like doing a mesh refinement study in finite elements. You can do a cell size study to make sure you've reached saturation. The next point is the aspect ratio. If you make a structure that is too tall, you're going to start to see some buckling or some out-of-plane bending that you don't really want to capture because, again, it's not representing your cellular material. If you make it too low, you're picking up a lot of the effects at the interface. So the contact effects could dominate the behavior. The ISO standard recommends keeping the height between 1 and 2 times the width, and I have no reason to disagree with that. So that's worked for us as well, so that's a good thing to keep in mind. Finally, the last thing, or two more things to talk about. One is the data interpretation. This is a typical plot you will get when you conduct a compression test, like this square honeycomb that we have compressed over here. And then people will say, well, what properties can you extract numerically, right? We don't like curves like this. We want to translate them into some numbers. And we tend to draw these plots like fitting a line that's an effective modulus, estimating maybe the peak stress before the first row of honeycomb cells fails. And then we may be interested in, there's a point which you can see just about now in the video where you reach densification. All the empty space between the platens is now taken up and you're getting the response of the densified material. Right around there, you could define a densification strain, or you could plot this line backwards and define the densification strain there. I've seen it done both ways. And you could be interested in the energy density, which is the area under the curve, which you could use a trapezoidal rule to estimate that area. A couple of things to point out is that the effective properties, stress, strain, they're effective. They are not point-wise material properties. So we have to be very careful in how we use them. And the one thing is that this shape will change a lot depending on what geometry you're working with. And it's difficult to get what we call a plateau stress. Some shapes it is easier, others it is difficult, which is why I tend to use the failure stress and just stick with that in my comparisons. Okay, so the last point that I want to bring out is strain rate dependence. And what we have noticed is that with cellular materials, you can get a sorry about that, my PowerPoint didn't like that video. It's restarting. It worked when we tested it, but I think I moved too fast. And I am going over time here. So if I cannot get to anyone's questions here, I'm sorry, I will get to them offline. So the last point I want to make is that there could be strain rate dependence in your geometries. And the reason for this is even though you are compressing your structure at a fairly low, you may think you're only compressing it at 10 to the minus 3 globally. Locally, you're generating high plastic strains. Or even elastic strains before you hit plasticity, because you may be seeing a lot of local beam bending. So if you're trying to if you're trying to just conduct a test at one strain rate and assume you are quasi-static, I caution you to conduct a few more tests, confirm that you are more or less quasi-static, as we're seeing right here at the very bottom for this particular curve, and then you can move on. So that's just another point I want to make, because we do see for the polymers and a little that there is this dependence. And when you get to very high strain rates, the failure mode itself is changing. So at relatively low strain rates, it is a material response. But when you get to higher and higher strain rates, you start to see at higher strain rates a collapse at contact, whereas at low to intermediate strain rates, you start to see multiple locations of failure initiate. So those are my 4 takeaways on the characterization standpoint. And the last section that I want to talk about is modeling. And I want to break this down into 2 simple ways of thinking about this. One is representing the material, and the other is representing the geometry. And of course, they come together in our development of something that is predictive. And I'm going to stick to mechanical modeling, so structural modeling as opposed to thermal or any other. And the 3 ways we can represent the material is one is to use bulk properties, consult a data sheet and extract bulk properties from there. The other is to do what we call homogenization and extract some kind of an effective property. So this is a typical scaling law that we may derive where the honeycomb, E, has a property that is a function of the material of the that constitutes the honeycomb and the relative density, which I described before. So you can derive these effective properties and then use them to represent the cellular material. And finally, you can extract properties at the level of a member. You can say, is there some way I can just take out that tiny beam out there and study that beam? And each of them has their pros and cons, and I just want to flash that slide and leave it there. Again, I'll be going into that in a lot more detail in the longer term class. But these are, broadly speaking, the 3 ways you can think about representing the material. So if you have an FEA code, it needs to know modulus, Poisson's ratio, yield stress, etc., depending on how sophisticated your model is. And these are 3 ways of getting those properties. The second aspect is geometry, and this is quite straightforward. You can use analytical models. We get a lot of insight from them. This is an example of a full-form beam theory equation for a hexagonal honeycomb that includes bending, axial, and shear terms. But you could also use simpler equations to estimate relative density. And once you've estimated relative density, you can derive these scaling laws. So there is some geometry information like thickness and length that is buried into your relative density. And then because that is captured in your relative density, you can essentially connect a property that you're interested in to a geometry of your interest. And the beauty of this is now you can say, if I change thickness, if I double thickness, what does that do to my modulus? Well, for a foam, it's going to be 8 times. If it's closed cell, if it's an open cell, it's going to be 4 times, and so on. So you can do those kinds of studies if you, 8 times. That's just the relative density. The modulus itself would change as a function of the scaling law, which you would fit experimentally. Secondly, you could do a CAD FEA. I don't think there's any surprise here. You can explicitly represent the geometry with CAD and import it in FEA and analyze it. So this is what we would call a full geometry representation model. The challenge, of course, is that it can be expensive, and folks are working to make that faster. I'll skip over this slide in the interest of time. And the one thing that I want to say on this slide is if we want to capture these kinds of details, like where the failure is occurring, what is the mechanism? Is it plastic hinging as it is for these geometries? We really have to do a full field FEA study. We don't get this level of detail from homogenization. So this is a summary of everything I spoke about, and this is really what that class is going to be about, which I'll talk about in a minute. And these are the 4 elements that I've tried to give you all a feel for some of the different topics within that. But really what I want to leave you all with and give you some time for questions is some resources. There's a very nice online class, a MOOC at edx.org that Professor Gibson, who literally wrote the book on cellular materials and cellular solids, teaches. It's free, and I highly recommend you take a look at that. That's where I started my learning. And then there are 3 books that I recommend for folks in the additive world: Cellular Solids book, Metal Forms, a Design Guide, and Cellular Materials in Nature and Medicine, if you're more interested in the biomimicry aspects of this work or applying it to scaffolds and implants. This is the class I've been talking about, and in many ways this was meant to be a sneak preview for this class. If you all are coming to MMX or were not going to come but can make it, I'm going to be doing a 4-hour class on October 29. This is in Youngstown, Ohio. It's $25 for members, $50 for non-members, and there's a link to register here, and we'll be reaching out to you all later with the link in an email as well. So this is where I'm going to elaborate over everything that I went so fast over in much more detail. A companion to that class is a textbook. So I've taken all the content that I've been writing about and studying and put it in an online wiki-like textbook. The beta version is going to be available to all the students of the class. It is tablet, mobile friendly, and it will be available to all America Makes members by the end of the year. If you want access early and are an America Makes member, send me an email. If you're not, unfortunately, we're only making it available to people that attend the class, and then you will have it for 60 days only. But this is what the class looks like, or the textbook looks like, and it's basically the companion to the class. So there are the same 5 topics I talked about today: introduction, design, manufacturing, characterization, modeling are represented there. And finally, I'll skip over this slide, but you can reach out to me for more questions and even follow us on our website, 3dxresearch.com. Quick thanks to America Makes, and PADT and ASU, my employers the last 5 years, and Entopology and ANSYS have been very helpful to us on the software side, and Professor Gibson for teaching that online course. And with that, I will hand it back to Ed.
All right, thank you, Drew. We'll now head into the Q&A session. We've got about 4 minutes left. As a reminder, please type your questions into the Q&A space on the screen. And I do have a couple questions that we can hit real quick here. Speaking of ANSYS, Drew, does ANSYS have lattice design optimization tools that you know of?
Yes, I know that the release 19 released one, but I'm not aware of the details around it. I'm looking forward to learning more about it. We have not explored it yet, but yes, they have got something that they've put out.
Okay, Drew, can you elaborate on the importance of strain rate dependence in testing cellular materials? How relevant is it for metallic lattices? That's
a great question, and I'll try and go back to that slide if I can. But we've noticed that the sensitivity to strain rate is much higher for polymers, as you would expect. But so far we've only tested electron beam melting structures for strain rate dependence, and we've seen mild strain rate dependence for those as well. So it is there, but at room temperature, it is not as strong as we see it for polymers.
Okay. Another question here. What is the difference between a lattice and a cellular material?
Oh, that's a very nice question. For a long time, I used to use the word lattice as a way to describe structures that are truss-based or have beams as their basis. So to me today, I think of lattices as a subset of cellular materials. I define cellular materials as a material that is constituted of repeating individual cells, and then each cell is some combination of material and space. So lattices then become a specific form of a volumetric 3D structure that uses beam elements to connect vertices. So that's how I think about them. I think of lattices as one of many cellular materials. And if I go off on a slight tangent, you could ask, what about foams? Because, where are foams in all of this? And I think foams are not really as relevant to the additive discussion. We can forms emerge through the forming process, and hence you have forms. So we use the word open cell form, closed cell form, but I think there is an implication that this was achieved through a forming process and is therefore stochastic or statistical in nature. So both those terms, lattices and forms, I think the form term we don't need per se. We can capture it with surface-based connectivity or beam-based connectivity, and the lattices are a specific instance of a cellular material.
Okay. I guess we have time for just one more quick question, Dhruv. Have
Yes.
you run into file size? Have you run into file size issues for CAD or G-code files?
We have not. We have not run into it for our experimental work because our specimen sizes are much smaller. We are running into it when we do structural level integration. So that fourth point I pointed out when we try and infill geometries. And, you know, there are several companies working on file formats to simplify that. And so I think it's a matter of time before 3D printers can interpret lattice-specific information. I know there are a couple of people on this call that could talk to this better than me. But yeah, so far we have not run into issues that, you know, just waiting a long period of time has not been able to resolve.
Okay, with that, we're right at the closing time. That'll wrap up this session of the TRX webinar series. I'd like to thank Dhruv Bhatte. If you have any further questions, or if I didn't have a chance to get to your questions in the interest of time, please reach out to Dhruv directly at the presenter contact information. There will be a post-webinar survey going out to all those who participated. We do really appreciate the time you take to provide America Makes feedback so we may continue to improve and strengthen the additive community. And a reminder that if you think you or your organization would be interested in sharing in the TRX webinar series, please reach out to me directly. Thank you for attending.